When it comes to this issue of Transplanckianism in my theory of gravity, there's quite a bit I want to say about it actually. And I think Transplanckianism, when it comes to quantum gravity, is likely to be unavoidable. And for this reason, people who are quantum mechanics aficionados, I think, very much steer away from any such notions and towards things like string theory, where the Transplanckianism isn't quite so apparent. But in the interest of keeping things very clear and simple, and crucially clear, and to try and understand in real physical terms what's going on, instead of going out into the wildernesses of mathematical abstraction, like I believe many physicists do, I'm trying to take it back to, well, not first principles, if you like, the first principle of gravitation that we have in modern times, i.e. Newton's law of universal gravitation, and see what the Newtonian force of gravity is between two hydrogen atoms in a 1 centimeter cubed container at a Lagrange point. So that number comes out as 1.86 times 10 to the minus 62 Newton meters cubed per kilogram squared. Now, that's a Transplanckian number. That would represent an amount of action that is substantially lower than Planck's constant. Planck's constant being about 6.64 times 10 to the minus 34 joules seconds, I think. Something like that. Some little prick on my YouTube channel decided he'd pointed at, how can you be submitting to nature if you don't even know Planck's constant? It's like, I don't know all the physical constants off the top of my head. I'm sorry. I know the speed of light in a vacuum, and that's the only one I know off the top of my head because it's 300 million meters per second. It's the easiest one to remember, and there's loads of physical constants, so basically. But yeah, I was in part motivated to do this video because this is something that Stephen Hawking came across as well when he was thinking about black holes and radiation and Hawking radiation, and he uncovered a Transplanckian problem for the wavelength of photons around black holes. He found that they started having wavelengths shorter than the Planck length, which is a real problem. I'm not so certain how he resolved it, or if he resolved it at all, or if he left that as an open problem, and one of the ways in which quantum theory doesn't seem to go together with general relativity, or ways in which quantum mechanics even might be incomplete, or ways in which, quantum theory might not be the gleaming, wonderful, incredibly well-tested, perfect theory that we have at the moment, because if it were the gleaming, wonderful, elegant, perfect theory that we have at the moment, we would never need to keep working on fundamental physics now, would we? So obviously it's not as cut and dry as that, it's not as simple as that. I'm going to go into what Hawking said about this, or I'm trying to find out what he did about it. So, a Transplanckian problem is nowadays mostly considered a mathematical artifact of horizon calculations. The same effect occurs for regular matter falling onto a white hole solution. Matter which falls onto the white hole accumulates it, but has no future region into which it can go. Tracing the future of this matter, it is compressed onto the final singular endpoint of the white hole evolution into a Transplanckian region. The reason for these types of divergences is that modes which end at the horizon from the point of view of outside coordinates are singular in frequency there. The only way to determine what happens classically is to extend it in some other coordinates that cross the horizon. There exist alternative physical pictures which give the Hawking radiation in which the Transplanckian problem is addressed. The key point is that similar Transplanckian problems occur when the modes occupied with Unruh radiation are traced back in time. In the Unruh effect, the magnitude of the temperature can be calculated from ordinary Minkowski field theory and is not controversial. Right, well that's a Wikipedia article, and I haven't yet been able to go into the ways in which the Transplanckian problem has been addressed before. Maybe they're using some kind of renormalization procedure or something, or something to bring it back to the Planckian realm, if you know what I mean. But I'm tempted to say that I think this non-Planckianism or this Transplanckianism might well be an observable quantity in the future. I'm tempted to say that in the future, or maybe the near future, even with very advanced and very sophisticated and sensitive instruments, at a Lagrange point, we may well be able to discover that there is a tiny, tiny, minute force there operating between two hydrogen atoms in a 1 centimeter cubed container, for instance, and that we really might be able to find instances where Planck's constant is actually violated as a minimum of action. So, this is sort of what the whole idea relies upon, or it's yet another prediction of my model. It doesn't rely on this necessarily, but I think that this is the truth. I think it's the truth that quantum mechanics is violated in a meaningful way, and that we're going to have to update and revise our quantum theories and go beyond quantum theory. And I mean, that's what we had to do anyway in quantum theory, I think, with the development of quantum field theory, and now we're in the second quantum revolution and so on. And I'm sure, like the likes of the people at Nature who bit back and rejected my paper were just kind of like old school types who can't accept newer ideas and so on, and newer modes of thinking about this most compendiously difficult of all problems, how quantum theory can account for gravity. And I figured out that the mechanisms by which it could, or the mechanisms by which it really ought to, I think, in nature, and sort of proven something, I think, that you can make it line up. The Newton's law calculation of the gravity between two hydrogen atoms and the calculation from Coulomb's law, you can make them line up. They seem to harmonise or be harmonisable and go together. And it does come out, both are Transplanckian though. Both results, I mean the one from Coulomb's law is 2.216 times 10 to the minus 68 Newton meters cubes, which is very, very, very much less than the Planck energy, isn't it? But then again, I mean, well, the Planck mass energy is about the same as that of a flea egg, isn't it, in terms of mass energy? So why do people think there's anything smaller than a flea egg in the universe? It's not like that. I'm very confused maybe about the Planck constant and what its physical significance is. Or am I, and I'm not getting this wrong, that Transplanckianism is totally acceptable? But it seems like Transplanckianism totally isn't acceptable in physics. Because it, I think of, Planck's constant representing a minimum of action. If you remove Planck's constant, or Planck's constant turns out to be false and incorrect, well, that's all quantum mechanics out the window now, isn't it? You have to start doing something else and something different. Something more classical, more like classical physics. Which mine really is. Mine's a very baroque, sort of neoclassical model of gravity. It just happens to include electrons. It happens to have a particle basis with a gravitational field. Which, I mean, is an idea that might excite some people, but, perhaps for a lot of people it would be too much against their ways of thinking, too much against what they've been taught. And, for that reason they wouldn't be able to accept it. But hey ho, I think it's worth sticking with, because I think but all sorts of reasons, supernova observations, beta decay, everything else. I do think it's the right answer still, so I'm going to stick with it.